Hello and welcome everyone. And this is our portfolio optimization workshop. So on this workshop, we will try to apply all the techniques which are covered in our portfolio optimization lecture series by using Hudson Thames Portfolio Lab Python package. So let's start with function imports. So as you can see here, we import various functions which you will need in this workshop, including standard libraries like pandas, numpy, matplotlib, Seaborn. We also use ML package, and of course we will import various functions from Portfolio Lab and get optimal number of clusters algorithm from ML which is used in nested clustered optimization algorithm. So let's start with the data. So we'll use the data which contains various ETF and bond, various equity and bond ETFs. And as you can see here, we have the range of one of the most liquid and widely used ETFs. So we can see here financial ETF, bonds ETF, TLTs, 20-year bonds, XLE Energy, S&P 500 ETF, what else? Utilities, etc. So now let's use this data set and take a look how various portfolio lab functions are applied to this data set of ETFs. So let's start with modern portfolio theory and mean variance optimization. So what we will do is initialize the mean variance optimization uh, object. And as you can see here, we use default value for calculate expected returns by using the mean value and the risk-free rate of 0%. So as we have previously discussed, in the world of zero or negative bond yields, it is quite well known and useful fact, used fact that the risk-free rate is assumed to be equal to 0 in the most of the papers. Now, let's start to play around with various functions from mean variance optimization. So let's take a look. So let's, for now, delete this condition and set the weight bounds to none. So let's start with the initial optimization problem we were talking about as a minimum volatility optimization. So what are the inputs of this function? So we use stock prices as inputs to mean variance optimization allocate method, which is a pretty much universal API for each optimization algorithm. We need to specify asset names by using stock prices columns. The solution is minimum volatility. Now let's forget about risk aversion parameter, which can be equal to any value for minimum volatility optimization problem, and we don't have any weight bounds constraints. So let's take a look at the output of this algorithm. So what we see here is that the output of this algorithm is contained in weights field, and we can sort the values of this field in descending order. So if we multiply it by 100, we can see here that actually the portfolio is quite concentrated. So we can see that almost all our portfolio allocations are in bond ETFs, and we have 9% of XLK allocated and almost zero allocations to other ETFs. That's actually kind of the problem we face in mean variance optimization, that actually the solutions are quite concentrated. So let's take a look how we can constrain our solutions in this case. So as we can see here, we can apply our weight bounds into mean variance optimization. And there are two ways to do that. So if you would like to apply universal weight bounds, yeah. So if you would like to apply weight bounds for each stock in your portfolio, you can set up a tuple with two elements. So the first element is the minimum weight, and the last and the second element is the maximum weight. So let's say that we want to have a minimum weight of 2% and the maximum weight of 30% in our portfolio, and still we minimize the volatility of our portfolio. As you can see now, the portfolio is not that concentrated. So we don't have 40% into EF or TLT in EF or TLT, but still we can see that the algorithm just gave the minimum possible weight to other stocks, and the portfolio is quite concentrated. So once more, this is kind of a problem of mean variance optimization, because actually quite often it does not yield diversified portfolios. So let's take a look at other solutions which can be applied in mean variance optimization. So here we can also use the inverse variance solution to generate to solve this kind of problem. As you can see here, it also has generated quite concentrated portfolio. And let's take a look at the other solutions in mean variance optimization. So we can also maximize Sharp. So still the portfolio is quite concentrated. We can use maximum diversification. So even though we use a metric of maximum diversification, the portfolio is still quite concentrated. So as I have also discussed, that if you would like to use either max return, minimum volatility, or let's say, for example, efficient return, or let's say efficient risk. So here you need to specify special parameter. So as you can see here, we can also specify the parameter which is called target return and target risk. So let's say that we would like to solve the problem of efficient risk and find the portfolio which yields, let's say, a target return of 10%. So as we have discussed, for a target return of 10%, we find the portfolio which yields the minimum volatility. So as you can see here, no optimal set of weights was found for this type of portfolio, and that's kind of a problem which can arise sometimes in mean variance optimization, that the optimal solution may not be found. And that's kind of a problem. So that's why actually critical line algorithm was initially developed, because it always guarantees that the solution can be found. As you can see here, we can also find the solution to problem of, let's say, max return, minimum volatility. And in this case, we need to specify the risk aversion parameter of our investor, which is lambda. Let's say it is 1. So for the risk aversion parameter of 1, we've found the so-called quadratic, what's called quadratic fitness solution. So here we can see that the portfolio is still extremely concentrated. Weight bounds equals to none. So we can see here that like it always yields a very concentrated solutions in this case. So let's take a look here and go back into the solution for minimum volatility. And let's say that we don't want 17% to be into IEF stock. So how it can be done? So as we have previously discussed, there are 2 ways to create weight bounds. So the first one is to apply weight bounds for all assets in our portfolio by specifying the tuple. But how can we constrain only some specific assets? And there is a construction which can do this. We need to specify a array which basically can generate inequality constraints. So we can see here that the weights of 12th asset should be less equal than 0.3 and more equal than 0.1. But how can we find the location of IEF stock in our portfolio? And there is a very good pandas function which is called getLog. So what we use here, we need to understand what are the integer index of IEF stock in our asset names list. So we want to find IEF stock here, and its position is 5. So let's say that the minimum weight for this stock should be 0.05, which is 5%, and the maximum weight should be, let's say, 10%. So we would like to find the minimum volatility solution, mean variance optimization solution, such that the IEF stock weight is more than 5% and less equal than 10%. So what we can see here is that actually the weight for IEF stock equals to 10%. So it is a scientific way to represent values. So as you can see here, it is 10% as it was as it was constrained in our weight bounds. So you can use modern portfolio theory to generate the portfolios based on your solution or your specific constraints. And you can actually use pandas to quickly generate a very interesting backtests. So let's say that we have created this specific portfolio, right? So how we can quickly generate the equity curve for that? So in order to generate the reinvested equity curve, you find the percent changes of your stock prices, you multiply that by weights, you find the sum over the 1 day, which yields you a daily returns of your optimized portfolio. Of course, in real world, you don't want to induce look-ahead bias in your portfolio optimization. You need to update your weights on a, let's say, weekly basis. So here we just use the whole data and found the optimal portfolio in advance on the whole data set and find how it would perform in past. But still, so we have found portfolio returns by multiplying stock prices percent changes by mean variance optimizator weights. We have found the sum over the axis, which yields daily returns. And now we find the cumulative product of those returns to understand how $1 invested in our portfolio will proceed over time. So as you can see here, this plot is the equity curve for a portfolio, which is represented by these weights. What we can also do is to plot the efficient frontier for our assets universe. So how it is done? So here we use we need to resample our weights on a weekly basis. So we use returns estimators. We calculate mean historical returns and specify stock prices and resample them on a weekly basis. And secondly, we need to calculate covariances. And still here we use returns estimators class and use calculate returns on a weekly basis. It generates the returns on a weekly basis. So let's take a look at this function call. So as you can see here, this function regroups our returns and find weekly returns of our securities. And after that, when we call covariance on top of that, we gave the covariance matrix for this particular asset universe. And what we see here, we can use MVO. It is still our mean variance optimization object to plot the efficient frontier with specified covariance and expected returns. So as you can see here, we have created the efficient frontier, and this plot generates the points where the minimum volatility and maximum Sharpe ratio portfolios are situated. So now let's go back into the critical line. Let's move further into critical line algorithm. So critical line algorithm is initialized. We can see here that the weight bounds are 0 and 1. As we have previously discussed in our lecture series, CLA algorithm can only induce inequality constraints, which are equal to all assets in our portfolio. So let's say here that our weight bounds should be more than 10% and less than 50%. And we still call allocate function for our CLA method. So we use stock prices, we use asset names, and we use a solution of CLA turning points. As we can see here, we can also use max sharp, minimum volatility, or efficient frontier solutions. Okay, so let's take a look. What's wrong here? We do it this way. Okay, so let's say, okay, so for this particular setting, this function generates error. So, but still, that is the way how to calculate the critical line algorithm and to solve critical line algorithm optimization problem. So you simply the API is pretty much the same as for mean variance optimization. So as you can see here, the function has generated a very strange portfolio, which basically invests all our assets into XLK stock. And if we take a look at our portfolio returns and just compare them to XLK stock dynamics, we can see that these two plots yield the same values. So actually our procedure to generate the $1 invested into portfolio works as expected. Now let's move further into denoising and detoning our covariance matrix. So as we have discussed in mean variance optimization, there is a problem with covariance matrices because number of data points which is used to estimate the covariance matrix is usually not enough to generate non-noisy covariances just because the number of assets is big. So here we face a quite well-known problem of dimensionality curse, which is a quite well-known problem in just machine learning, not only financial machine learning. And there are several ways to solve this kind of problems, which is detoning or denoising our covariances. So let's take a look how a portfolio that functions work to solve this particular problem. So denoising and detoning functions are implemented in risk estimators class. So now let's find the original covariance matrix. So we find the covariance of our stock prices percent changes. And now let's take a look how denoising works. So as you can see, our risk estimators object has a function called which is called denoise covariance. And what we can see here, it takes several parameters as inputs. So the first one is the original covariance. The second one is TN relation, our denoise method, where they would like to also detone our covariance matrix. So detoning just basically extracts market component out of our covariance matrix. Market component, if we want to denoise our covariance matrix, so if we would like to detone our covariance matrix, as we have previously discussed in our lecture series, we need to specify the market component in our eigenvalue decomposition, in our PCA decomposition of covariance matrix. So usually, in the most cases, market component is our first eigenvector of our covariance matrix decomposition. But sometimes probably you may have a very specific covariance matrices, and you can specify. So we can also specify kernel density bandwidths, which is used in kernel density estimation, which is used in constant residual eigenvalue denoising algorithm described by Marcos Lopez de Prado. And the final one is alpha. So alpha is used in target shrinkage method. So let's repeat it once more. There are three ways to denoise our covariance matrices, which are implemented in Portfolio Lab. So the first one is constant residual eigenvalues method, which is described by Marcos Lopez de Prado and his paper, Efficient Frontier Robust Estimator. And this parameter needs your covariance matrix, Tn relation. So Tn relation is simply the number of data points which are used to estimate the covariance matrix divided by the number of assets in your matrix, which is basically, as you can see here, the the number of rows of our stock prices divided by the number of columns in our stock prices matrix. So denoise method. If you like to detone, you should specify true. If you detone in your covariance matrix, you need to specify your market component. If you don't do this, we assume that the first market component is used in detoning. You need to specify kernel density bandwidths of eigenvalues estimation. Alpha does not play any role in your constant residual eigenvalue denoising. So alpha is only used in your target shrinkage method. So let's take a look at how constant residual eigenvalues method works. So we use covariance matrix, Tn relation, and let's specify alpha here. So as we have discussed, alpha does not play any role in our constant residual eigenvalues eigenvalue denoising algorithm. So detoning equals to false. And now let's create denoised covariance. Here there is a very good function also, which converts a covariance matrix into correlation matrix. So let's do this. So let's convert original covariance matrix into correlation matrix and also convert our denoised covariance matrix into correlation matrix and plot the difference between these two matrices. So that's what actually we do. And we plot the absolute, so we plot the heat map of absolute differences between our original correlation matrix, which was constructed out of our covariance matrix, and our denoised correlation matrix, which was created from denoised covariance matrix. So as you can see here, there are pretty serious differences in denoised covariance matrix. So now let's specify alpha of, let's say, 0.9. And let's take a look if our plot has changed. So as you can see, there are zero changes in our plots when we change alpha, because alpha is only used in your target shrinkage method. So now let's take a look at how target shrinkage method works. So let's say that we use target shrinkage denoising method, and let's say alpha equals to 0.2. So here we can see that the target shrinkage method generates a different denoised covariance matrix, and by changing our alpha values, the value of our the difference between original and denoised correlation matrix starts to modify, because alpha impacts the way you denoise your covariance matrix in target shrinkage method, but not in constant residual eigenvalue. Now let's take a look at how detoning works. So let's go back into constant residual eigenvalue, and detone equals to true in our denoising method. We say that our market component equals to 1. So the first eigenvector contains market component. And let's take a look how correlation matrix changed. And now we can see a massive change in our correlation matrix, because when we extract the first component out of our covariance matrix, we extract so much information from it. Because if you take a look at the PCA, the composition of covariance matrices, usually the first market component explains somewhere around 60% of variance in our covariance matrix. But on the one hand, it explains lots of variance. On the other hand, it's like a loud tone, as we have discussed it in our lecture series, right? So when we extract this market component, our matrix changes significantly, because we take away a very big but sometimes redundant piece of information. So as we can see, our correlation matrix has changed massively when we detone it. So usually detone correlation matrices can be very useful in clustering, in solving clustering type of problems. So now let's take a look how to use theory applied and how to use and create theory applied correlation matrices. So first, what we need to do is to, let's say that we use GICS classification. So this is the way we create this data frame. So we see a, well, let's say a high level type of our asset, its region. So you can see that like the type is 1, 0, the region is 1, 0, 1, 0, the sector is 1, 0, 1, 0, 1, 0. So it should be, so the data frame you create, which is your fundamental view on the way clustered, the way assets are clustered, should be such that that's, for example, you have a high level region, lower level region encoded, etc. So let's say, for example, XLU, its type is 1, 0, region is 1, 0, 3, 0, and here we can see 1, 0, 3, 0, and 60. So that is the format which is expected by theory implied correlation matrix from a classification tree for theory implied correlation matrix. So we still use here theory implied correlation and apply a function which is called tick correlation, which basically uses the original correlation matrix, your tree structure, which is here our GICS classification. It also uses TN relation and kernel density bandwidth to denoise our covariance matrix. And now we can create our theory implied correlation matrix and find the difference between theory implied and original correlation matrix. So here we can also see that the difference is quite substantial, because by adding not all, we have added our economical and fundamental view on the way assets should be clustered and combined it with our empirical views on correlations, right? So now let's move into a machine learning type of algorithms, which is nested clustered optimization algorithm. But first, let's take a look actually how the core of this algorithm works, which is optimal number of clusters algorithm. So optimal number of clusters algorithm is implemented in ML FinLab package. So here we can see from ML FinLab clustering import get ONC clusters. And it takes your original correlation matrix, a number of k-means initial data points inputs, so number of random centroid initializations in k-means algorithm. So let's apply this algorithm and take a look at output of that. So what it does, it outputs your original correlation matrix. But what is the most important is those clusters which were generated by the algorithm. So as we can see that what we have seen here is that algorithm thinks that the optimal number of clusters here is 2, which are basically both bond clusters. So here we see that in 0 cluster are bond ETFs. And in the first cluster, we have, in cluster number 1, we have equity ETFs, right? So these are the inputs of our optimal number of clusters algorithm. So now let's take a look how nested clustered optimization works. So we initiate nested clustered optimization, which is import that from Portfolio Lab package. And we just create NCO weights by calling NCO allocate NCO method, which takes your covariance matrix as inputs, your maximum number of clusters. So here you can specify either your own maximum number of clusters, or if you use none, the algorithm will use optimal number of clusters algorithm and number of initialization of this algorithm if needed. So let's take a look what are the results generated by this algorithm. So as we can see here, our algorithm has generated a long short portfolio because in the original implementation, there are no constraints on a fact that your portfolio should be long only. And here we can also generate the portfolio returns of the portfolio which was generated by nested clustered optimization algorithm. You can actually specify a maximum number of clusters, let's say 7, which can be your fundamental view on the way assets are the way assets are clustered. And we can see that the output of this algorithm is pretty much the same, right? So yeah, so that's how nested clustered optimization algorithm works. And now we can move to another portfolio optimization algorithm, which is hierarchical risk parity. Now let's take a look how hierarchical risk parity algorithm works. So we initiate the hierarchical risk parity algorithm, which basically does not have any input parameters in its class constructor. And now we can call allocate method first. So we call the allocate method, which takes your covariance matrix as input. And here, what you can actually specify, you can specify lots of different things. So usually, I would suggest to go with a simple covariance matrix and to play around with a linkage, which can be either single, which is the original implementation, complete, average, or word. But actually, we will take a look how to play around with various distance matrices used as inputs for HRP and how to input nonlinear dependence matrices as input to hierarchical risk parity. But now let's start with simple allocate function from hierarchical risk parity, which basically applies to covariance matrix and the linkage method of word. So what we can see here that the algorithm has generated a portfolio, and now we can backtest this portfolio by using the method we have previously discussed. So let's take a look how single method works. It generates a different output, but we can see here that we still have a quite serious overweight for bond ETFs. And there is a way how we can constrain that in a hierarchical risk parity algorithm. So first, you call HRP allocate method, and after that, you can use HRP applied weight constraints method, where you just need to specify a dictionary with a ticker of your asset and a corresponding tuple of maximum weight and a minimum weight. So here we say that the minimum weight of BND and CSJ is 0 and the maximum is 0.1 for both of them. So other assets are not constrained. And now we can see that actually our algorithm did as we have expected, that the weight for these two ETFs do not exceed 10%. So let's generate the backtest for this portfolio. So we can see that the equity curve has changed a bit. But now let's say that we don't want to use linear Pearson correlation in our hierarchical risk parity algorithm. So how I can do that? So let's start with a function from ML Theme Lab, which create the dependence matrix out of your stock prices data frame. So here we can see that we use our stock prices data frame as input, but instead of that, it is a mistake. We should use a data frame as of stock prices percent changes, and the dependence method is mutual information. So first, we need to create a correlation matrix, which is not correlation, but basically a dependence matrix, but it was calculated by using a nonlinear dependence matrix, right? So we do this by applying ML-FinLab's codependence get dependence matrix function. And after that, what we do is that we convert this correlation matrix into distance matrix by using ML-FinLab codependent get distance matrix, where the input of this function is our dependence matrix from previous function call. Okay, so we should use drop an A. Right, so now we have the distance matrix. So what we can do here is that in HRP, we specify that we use a different distance matrix, which will be used in your assets clustering. So here, if you would like, let's say, to use denoised or detoned covariance matrices to cluster your assets in HRP algorithm, what you can do is to first use covariance matrix, denoise it, detone it, convert it into correlation matrix, convert correlation matrix into distance matrix use it as input in your HRP allocate method. But still, you need to specify asset returns, which will be used in inverse variance correlations. So on the one hand, you will use the estimation of variance by using a simple covariance and volatility in Pearson terms, but you will cluster your assets by using a nonlinear dependence matrix, which is converted into distance matrix. Because at the end, our agglomerative clustering algorithm takes distance matrix as input. So let's apply this function and take a look how our asset returns have changed. So we can see here, so the return, the final return is around 1.20, and here, so when we specify nonlinear dependence matrix, we really get a slightly different result compared to Pearson correlation matrix. So this is a very flexible algorithm implementation, which lets you, on one hand, still use inverse variance allocation technique by specifying your asset returns in percent changes. So here the algorithm will use these percent changes to calculate the variances of your assets. But on the other hand, you can use your own distance matrix, which is calculated and created out of your dependence matrix, which you would like to use. So here, for example, what we can do, we can use our zero implied correlation matrix we have calculated previously. So the distance matrix. Okay, so we have created zero implied distance matrix. Oh, actually, we can use our zero implied correlation, right, as input for distance matrix. So we will convert our zero implied correlation into distance, and now use this distance as inputs to our HRP algorithm. So here we can see that still the performance of our algorithm has changed quite substantially. So what we now can do is to use denoise or detone covariance as input for our HRP algorithm. So let's say that we detone and denoise our covariance matrix by using the constant residual eigenvalue method with a kernel bandwidth of 1,000, and we create the modified covariance. Out of that, we convert our modified covariance into modified correlation, And out of that correlation, we create the distance matrix. We use this distance matrix as input to our HRP algorithm, and still we will use our original covariance matrix to calculate asset variances in inverse variance allocation method. And now we can see that the algorithm worked well and generated a new portfolio, which is quite different compared to other algorithms. So this function actually does what we have previously did. It uses our theory implied correlation matrix as input for our clustering algorithm in hierarchical risk parity and generate the backtests. And now let's move to the final part of our workshop and take a look how hierarchical equal risk contribution algorithm works. So it takes confidence level as input, but it will be only used in your conditional drawdown risk. So if you use a risk measure of conditional drawdown risk only, so if you use, let's say, equally weighted or other risk measures, confidence level is also used in conditional in expected shortfall calculations. So we initialize our Herc class, and here we can actually, the API is pretty much the same as for your hierarchical risk parity algorithm, with a slight difference that you can specify optimal number of clusters, because here the a little bit different clustering approach is used. We have previously discussed that in our portfolio optimization lecture series. So you can either specify optimal number of clusters which you would like to use, or you can use none value. And in this case, gap method will be used to find the optimal number of clusters. You can specify the risk measure, which can be either conditional drawdown risk, equal weighting, variance, standard deviation, or expected shortfall. We here specify asset names and stock prices. So the Herc algorithm did a job. You can actually, you can also play around with linkage methods. And here we have generated a portfolio. So let's say here we would like to use equal weighting scheme. So here you can see that the portfolio generated actually two clusters. The equity one with equal weightings inside of this cluster, and another one, this cluster with equal weightings in this cluster, and another two clusters. And here you can actually see how Herc algorithm is different from HRP, because inside of this cluster, instead of just naively splitting our assets into twos, as it is done naively in HRP, the algorithm just allocates equal weighting scheme to the whole cluster, despite of number of assets in it. So in this case, the algorithm is staying true to its dendrogram and clustering structure, right? So, and right now we can backtest our portfolio. So in this workshop, we have discussed how to apply Portfolio Lab library to generate and use mean variance optimization, critical line algorithm, how to denoise, detone your covariance matrices, how to create theory implied correlation matrices, how to use them as inputs for your hierarchical disparity algorithm, how to use nested cluster optimization. And in the final part of our lecture series, we have discussed how Herc algorithm is implemented in Portfolio Lab and how to use its implementation to generate hierarchical equal risk contribution type of portfolios.